The next concept that I want to introduce is precision. What do we mean by a precision of a medical instrument? What does it mean for you to design a medical instrument that is precise, or for you to buy an instrument and understand its precision? Now, it turns out there's actually more than one way to define precision. So I'm going to give you the way we're going to be using that term in this class. But I want you to be aware that there's, you'll see different definitions for precision. I'm going to define it as the, let's call it the decimals on the display, or the smallest, this is probably better, increment on the display. Maybe neither one of those are clear, so let me give an example. You have a temperature meter, right? Like the kind you get, I'm going to exaggerate this side of it. The kind you get at CVS. So here it says temperature. Let's say you have it set to degrees C. It has 1 digit, 2 digits, a dot, and then a third digit, okay? In this case, right, and this is in degrees C. In this case, we would give this device a precision of 0.1 degrees C, because that is the most that it can report, the most that it can resolve, right? You buy a laboratory grade device, right? It's a fancier device. And it has, 1, 2, 3 decimal, 1, 2, 3. Then this device precision is going to be 0.001 degree C. 2 instruments. This one has more precision and this one has less precision. All displays, you can imagine, right? Whatever we add, all displays will have some level of limited precision, right? You can't have infinite precision. And it turns out and this may seem like a silly point, but it ends up being really essential, right? It turns out our voltmeter also has a limited precision, right? You may have settings on it where you can adjust it in order to increase that precision, but there's a limit. So let's think about that. Let's say we have our voltmeter. And where does our voltmeter go? Our voltmeter goes right here. So let me draw it in. Now we're going to talk about our voltmeter. And let's say it had a precision of 0.1 volt. And so that means that on the display, it shows you some value, a point, and another value. Right? So those values could be anything, right? It could be 0, 5, 2, right? Or 10.7. Every voltmeter is going to have that limitation. And as we go on through the course, we will also understand that every device that converts your signal into the digital world, what's called an analog to digital converter, will also have an internal limitation. So this is a very generic concept, but we're going to start with, to get intuition about it, we're going to start with this example of the voltmeter. All right, so our voltmeter is limited. Okay, no problem. That's what we know. Well, now let me create, I want to create a problem for you, right? You have your voltmeter, you have designed your circuit. You happen to have a sensor, you picked your fixed resistor and all that, and this is how your design works. We will consider this here. This is now your design, your implementation. Let's talk about what your implementation does. When the temperature is 25 degrees, the voltage out is 5.01. Why is it 5.01? You know, it's a function of whatever you picked here and what you picked here. At 30 degrees, which is a pretty big difference, the voltage is 5.05. Now, why does it, look at the previous lectures, right? Why does it change? Because when the temperature changes, the resistance changes by some amount, and the resistance change will change the voltage out by some amount. Now, I'm skipping, right, ... I'm skipping what the particular features happen to be, right? I'm just saying this is how you made it. This is how you designed it, right? Great. What's the problem? Well, it's 5.01 volts. Now let's go to your, sorry, I should call this what I call the V sub S. Let's look at what you measure. Well, if it's 5.01 volts, you don't have that extra bit of precision, right? You essentially will be sampling up to, let me draw it out, up to here, right? It's like having a tape measure, right? But it has inches and not sub-inches, right? You can only measure up to what your instrument allows you to measure. So in fact, in this situation, you would measure 0, if you want to be explicit, 5.0. You wouldn't see this one because your voltmeter doesn't have enough precision. What would happen in this case? You would measure 0, 5.0. And there we have our problem. Right? You've made an instrument. It's 25 degrees in the room. And you measure 5 volts. It is now 30 degrees in the room. You measure 5 volts. You measure your aunt's temperature, right? Let's say this trend continues. You measure 5 volts. Your cousin has a fever. You measure his temperature. You measure 5 volts. You can see that's not useful. You know, I wrote here the display should have an indicator of the measurand. I should add a big qualifier here. Is useful with 1 L or 2? 1. It should be a useful indicator of the measurand, right? I mean, this is an indicator. I think that if the temperature went to minus 100 degrees C, you might see something change. But it's certainly not useful for the purpose that you have made it. Is that clear? So, what's the solution? Well, in this case, well, and to be clear, once you took this measurement, right, your next step I'll fit it in here, would be to calculate the temperature, right? You would use this and use this in order to calculate the temperature. And how would you do that? Well, you would go through this process that we just talked about. But what you know is that you'll calculate the same temperature because you're starting with the same voltage. So you're going to miss. You're not going to get it right. Because in this case, you will calculate something. Let's say it's 20 degrees. And in this case, you will also calculate 20 degrees. Right? So even if we take this to the next level, you have now made an instrument that says it's always 20 degrees. Is it working? It's working, but it always reads 20 degrees. It is a limitation of the precision. Now, what is a solution? What do you guys think? Quit? Quit. Instrumentation is not for me. What's a solution? Go ahead, what about the precision? Okay. So one solution, I think the very natural first suggestion is get a better voltmeter. Right? You can get a voltmeter, right, that measures out to, right, the 100th, right, to the second point. And so now, in fact, that voltmeter would report 501 and 502, right? So that is a good solution, right? It might fail us, however, right? As I'm sure you're aware, if we go on to a situation where from 30 to 35 degrees C, right? I'm running out of room here, but I'll write it. We get to 5.051. Right? So from going from 30 degrees, I wrote it sloppily, but I'll say what I wrote. If going from 30 degrees to 35 degrees, you go from 5.050 to 5.051, then we once again don't have enough precision. Right? So then you would say, well, just get another point and another point, right? And so you could say the solution is to have a device that has tons and tons and tons and tons of precision. Right? It's like a display, right? Right? It's like a really, really long display, right? That has a lot of, or that so you can somehow scan it, right? Which wouldn't work here. It wouldn't be difficult on a computer screen, right? To show a long value. And that is a good solution, right? However, it may be the case that the changes are so small that it's still not enough, right? And so while I think it is a good solution, right? A parallel solution, right, would be possibly to redesign your circuit so that these voltage changes are bigger. Right? That would be a parallel solution. So in this case, we have a new circuit. Right? And we'll call this circuit, design V2. In this circuit, it is, well, let's do the same thing. It's 5.0, I think it was 1 volts at 25 degrees, and it is 5.50 volts at 30 degrees. In this situation, even with the original meter, we would measure 5.0 and 5.5 volts. Right? With this new circuit, and we talked about last time exactly what you need to do. And remember, the emphasis here has always been not the largest voltage, the biggest change in voltage. And now you know why I'm emphasizing that, right? Because if this was 1,000 0.00000, and this was also 1,000, 0.0000001. Those are huge voltages, but that's not the point here. We're really, and in fact, that can be counterproductive, but really the point is the change in voltage. So here the change is almost 0.5 volt. And in fact, we measured the 0.5 volt. Right? So you can increase the precision, or you can design your circuit. If your initial circuit design is so bad, right, that it goes from 5.0000001 to 5.00002, you're going to have a very hard time dealing with it on the precision side. And that's even before we talk about something called noise. And so it is a smart idea to design your circuit in such a way that you have a nice voltage change. It's going to make your life easier, whether you're looking at it on a voltmeter or whether you're ultimately doing something with it in order to actually display the degrees. Make sense? All right, now I've created another problem though. This was 5.50, 5.5, very nice. This was 5.01, oh, but we cut off the one, right? We cut off the one. When we're looking at 5.0, we don't know what came afterward, right? It could have been at this point, it could have been 5.04, 5.03, I don't know. You know, right? You know, but if you're actually sitting here making the measurement, you don't know what came afterward, right? You've lost that additional bit of information. Does that make sense? So now the question is that a problem? Is it a problem? You could say, maybe. So I'll go back to this situation, right? But then maybe you should add another one just in case, right? You know what? Add 100, add 1,000, right? You should be measuring 5.000123000, right? Go on and on and on, right? Of course, no matter how much you go, there might always be more, right? So it's correct that one solution is to add more, but you still got to tell me one more, right? 100 more? So what do you think? Does it matter or does it not matter? Yeah.
I think up to a certain point it matters. So maybe like we can get 3 places after the decimal, and that's like, okay, this is valid. And then I guess it also depends on what you're measuring, because like for temperature, let's say, you don't really care after a certain point. You're like, okay, this is 96.4.
Right.
Recognize that. But then for something where it's like, okay, if this is even 0.00001 above the threshold we want, it's gonna explode. So you want to be more precise.
Okay, so your answer was, and it's the perfectly correct one, is it depends. But specifically you're saying it depends on what the purpose of the instrument is and what it is that you're measuring. If I'm measuring the temperature of my son, I don't need to know, right? Whether it's 37.1 or 37.100000001, right? If I get to 37.1 and that's correct, I have enough information. And so the answer to this question is not answerable without going back to the initial problem and this concept of usefulness, right? It's an interesting notion. We've come full circle, right? Usefulness. It is possible, so to be specific, by adding more and more measurements here, right, we will have a more detailed number, and we will calculate a different temperature. We will, right? But at some point, it doesn't seem to be making much of a difference, because in one case, we're calculating 37.01, and the other case, we're calculating 37.01000000. But the other point you mentioned is, there actually might be an application where it matters. Perhaps we're chemical engineers and you're making some sort of reactor, and that difference of a fraction of a degree will make a difference about whether it blows up or not. We're getting at an issue that is at the absolute core of biomedical instrumentation, okay, through this example. So we'll talk about that next.